Thank you very much. It was time to get back to industry after 10 years in academia, but they wouldn't let me go, so I'm now in both places. But I thought Curion was a good conference to be at because it's meant to do both industry and academia. And, well, I am both. I've been both. So I have some opinions on that. Furthermore, it's supposed to be on sort of practical side as opposed to pure theoretical. That's also a favorite of mine. And this is officially the PLE keynote. So it's about evolution and how languages grow and which constraints there are and how it works. And so I have a list of things that I'm talking about. It's a C++ talk. I'm not talking about languages in general. I'm trying not to boast, and I'm trying not to make any apologies. If something sounds like an attack on another language, then I slipped up and I apologize. I try not to. And I'm definitely not just going to do language technicalities. I'm looking at sort of overall lessons that might be useful in development of languages, C++ and others. And that's it. And towards the end, I hope we can get a discussion. There's lots of people in here, and it's hard to have a good discussion in a large room, but I think we'll succeed anyway to judge from questions and answers and other things. And no, I don't know all the answers, and there is no one best language for everything and everybody. If you believe that there is such a thing, you will get an argument from me, even if you think that language is C++, because there is no such language, and I don't think we are going to see one in our lifetime. So I'm going to talk about what C++ is and why. And then I'm going to attack some myth and make some social and technical points. And then finally, I'm actually going to show some code, because I think I once in my life gave a talk without code, and I felt like such a fraud. And I felt that this was really unpleasant, and there was only arm waving, so there has to be some code, otherwise it isn't real. And then that's where we do a case study. I really wanted to do two. I'll do one, and the other one you can listen to tomorrow. And a different thing. So basically, let's set the scene for where C++ came from and why and such. The early 80s, I actually started in '79, but basically, Ken and Dennis had just proved you could write portable systems programming. At the time, everybody knew it couldn't be done. I was suggesting to write a portable distributed operating system for my PhD thesis, and my advisor says, well, you probably can't do it. And he was, of course, right. But one of the reasons was that people were writing these things in assembler. And it was still well known that things like operating systems, you had to write in assembler. Things like compilers, you had to write in assembler. That was the thing. You went and look at C. C didn't have function prototypes. You couldn't say what arguments a function took. So square root of 2 was a really good way of crashing your machine, because square root wants a double. You gave it an integer. The call point didn't know what the function wanted, and you crash because you get a floating point number that's not normalized. So this is a very primitive world. The lint was a state of the art in static analysis. Of course, there's places where these things are not true and not general. There's a research lab here. There's a language there. There's a firm there that is not like this. But this was roughly the way the world looks. Most computers had less than a megabyte, not gigabyte, ran less than 1 megahertz for cycle times. PDP-11 70s were really cool. They were, really. I mean, they are a small, small fraction of your cell phone's power. Very small fraction, like 1,000. But they were cool and nice, and you could have 40 people editing full speed, compiling full speed, and you never saw an echo delay, right? Why can't we do that today? Anyway, VT100, some of those have heard of them. They make rather good boat anchors. That was for screens. The PC was still in the future. And furthermore, I'd been using Simula for a while, and I was reasonably keen on object-oriented programming, even though I never used the term because I was allergic to hype. And anyway, the Norwegians called it object-based programming before somebody redefined the terms. But anyway, everybody knew that it was too slow, too special purpose, and you had to be a genius to write object-oriented programs. I mean, real programmers just couldn't do it. This was well known by the 99% of the industry that had actually, well, 99% had not heard about object-oriented programming, but among the ones that did, most of them had this opinion. In particular, it took me several years to convince people at Bell Labs that virtual functions was a good thing, and class hierarchies was a good thing. I mean, the thing I heard was, if you want a virtual function, you can't have done your analysis right. You want to call a function and you don't know which one it is? I mean, there must be something wrong with you. Anyway, so if some of the things sound strange, that you had to invent something that basic, or something that has been there and everybody's been using since you were born, well, there was a time where it wasn't so. And my contribution has been to help people out of that hole. So basically, C++ comes from two sort of intellectual traditions. Down here, we have the close to the hardware thing. A direct map to the hardware is really important. You start out with a simpler one-to-one correspondence between what you say and what instructions are in the memory. Everything manual. That's David Wheeler there, was my advisor in Cambridge. He's one of the 10 people who can claim to have invented the first compiler, and did GZIP2, actually did the algorithm, the Burroughs-Wheeler transform, and a few other things. Really nice guy. But so he actually also wrote the first program to run on a stored program computer. So we start with there. Every byte counts. Every cycle counts. And from there, we go to BCPL, to C, that's Danish Ritchie, of course. And this is, if you want to write a device driver, if you want to write a memory manager, if you want to write a scheduler, you sooner or later get down there. But it's cold and unpleasant down that close to the hardware. Objects are of a fixed size, for instance, and they don't have any types and other horrible stuff like that. Here, the Fortran came the greatest improvement in programming so far, which was the idea of, instead of writing to the machine, writing in some language that was fit for humans. I mean, very peculiar humans and very peculiar language, but it was aimed at humans, expressing things ideally the way they talk about it, the way they write it on their blackboards. Whiteboards hadn't been invented yet. And basically making it for the humans. And had a side effect, which I think was unintentional, things became portable. Because if you write in the language that is suitable for you and for talking to your friends with, it doesn't actually care whether it's on an IBM or a UNIVAC. I'm sure that embarrassed IBM who paid for the whole stuff. But we got portability by lifting the abstraction level. And then soon everybody wanted a language like that. We had the engineers and scientists had Fortran, the business people got themselves COBOL, and very soon there was about 200 of them. And the problem was you couldn't talk from the one to the other. And that's where the Norwegians, that's Christian Nygaard, which is indirectly the cause why I'm here this week. But he actually taught me object-oriented programming. But he came up with, together with others, but he was a key person in getting the idea, like, why do you put these abstractions into the languages? Why don't you let people define their own abstractions, putting the abstraction mechanism into the language? Because what you found was that a Fortran programmer couldn't talk to a COBOL programmer, totally different language. And they couldn't, their programs couldn't talk either. So if you wanted to read a whole bunch of records from, say, a magnetic tape and do some computations on them, you really couldn't do it in any reasonable way, because the records and the tape stations were COBOL territory, and the numbers and computation was Fortran territory. So if you could build a general purpose language where you could build in your own abstractions, then you can actually fulfill the promise of that by allowing you to write. I can write a record abstraction, and then I can write a matrix abstraction, and now I can start computing over the data from the records. This is, of course, very simplified, but that's the basic idea. And I found myself in a situation where I would like to write code with a reasonable abstraction level, get me away from the hardware. But I also needed to manipulate the hardware. I needed to write that device driver, network driver, memory manager. And so I put the two together, C for the memory model and Simula basically for the abstraction model. And from there, a lot of stuff happened. So basically, I can explain C++ in 2 lines, 1 slide. It provides a direct map to hardware, basically instructions map to instructions, memory references map to memory references, not complicated access structures, and nothing complicated there. Initially it came from C, and it's still quite compatible with C. And zero overhead abstraction. The idea from classes and class hierarchies came from Simula, and what I was doing was to get them to the point where you didn't have overhead from actually using them. There's no extra overhead from using a member function, from using a freestanding function, and if anything, you can just inline the whole thing and it goes away for runtime. So this was important. I've been running on machines where a function call took a function call and return took longer than taking an interrupt. Now you have a choice. You either get absolutely zero overhead for crossing a protection boundary, or you lower your whole program to not use something as advanced as a function. So I have to deal with that. So by zero overhead, I really mean zero, not a byte, not a cycle. And obviously not every program requires that. But at the bottom of all of our systems, there are something where this kind of stuff matters. So C++ is for things that has a combination of need for performance, need for being close to hardware, and complexity, so you need mechanisms for handling it. That's what it's for. And much of the inspiration came from operating systems. And sometimes I'm asked, in some words of other, what does C++ want to be when it grows up? And the answer is, it wants to be better at that. That's its niche. It's a large niche, but it doesn't try to be everything for everybody. If you have the kind of problem, building software infrastructure, manipulating hardware, then it has something to give there. And I actually have a book written explaining modern C++ in 180 pages. So this is a 1-slide version, 2 lines. The longer version, you can actually get the whole thing, including the standard library, in 180 pages. So what do I mean by the map to hardware? An operation is an operation. A plus is a plus. So if you do add 2 integers, you get the machine's integer. If you add 2 double precision floating point numbers, you get the instruction there. There's good things from that, there's bad things for that. But you run on the hardware flat out. basically there's value types, and there's handles. Value types can be built in, or you can build them yourself. Handle types are all built with the abstraction layer. And objects are mostly constructed by simple composition. If you take two integers next to each other, well, you can call that a point and provide all the operations to it, and there's no extra overhead. And you can stick those points on the stack, you can stick some points on the free store, things like that. And so you can compose, and everything maps directly onto memory. That's the C and the C++ memory model, and it's useful. There was some early design decisions, and I'd like to emphasize them here because we're trying to start, and then we'll see what happens. But basically, C compatibility was important. I really didn't want to make my own mistakes in basic things like defining a loop. First of all, Dennis was very smart and probably would do it better than I did, and he had already done it. So why would I prefer my mistake, or why would you prefer my mistake to his mistakes? And we know his mistakes. So we'll stick to that. Also, there's a very nice book describing how to write a for loop and how to declare an integer. So I didn't want to touch that. It's important to be compatible with something, but I couldn't live without function declaration, so I put those in. But the principle was leave no room for no language below. I mean, so if you can always write a few lines of code in assembler better, but a few lines, you can't write a real system in assembler and do better than C or C++. So that's the C compatibility, the C memory model. The similar classes and class hierarchies came in, but I did a few things like objects are treated uniformly. I don't care from the type system point of view, from the allocation scope point of view, things, whether you designed the type or I did. They go to the stack, they go to the free store independently. Pointers point to them independently of who defined them. I wanted generic types and operations. Of course, when I was building a vector, I wanted a vector where t was a parameter. And I got it badly wrong. I recommended the use of macros for that. And I don't recommend the use of C, C++ style macros for anything. They spoil a lot. It's one of the reasons we don't have decent programming environments for C++. They're coming, but we should have had them 20 years ago. And macros are the main reason. The human and the compiler looks at different information, and that's not good. Constructors and destructors came in. A constructor establishes the class invariant if you have one, and acquires necessary resources to run. I have a quote in my notebooks from 79. That was where they were for. And of course, since we acquire resources, we have to give them back again, and that's why we get destructors in place. Otherwise, I would have to plug in a garbage collector, and garbage collectors don't actually work too well when you're, say, building a garbage collector. You get yourself into a thing. Also, of course, this works on the real machine. This is the kind of stuff you use if you're building a virtual machine. And concurrency support was put in the libraries, because I just gotten myself a PhD, mostly in concurrency and distributed systems, and I reckoned I knew about 40 ways of getting it wrong, and none for getting it right in general. And this has actually served us reasonably well. C++ 11, C++ 14 has a mixture of intrinsics and library support that deals with this. Anyway, that was what we're doing. Later, overloading came in a couple of years later, most for constructors and assignment, and then actually for things like subscripting and application, how you make function objects, which allows you to wrap an operation. Exceptions later, templates, multiple inheritance. Okay, let's go further. So let's see, what have I learned partly of this? One of the things is that If you just list a set of language facilities, you have lost most people before you get to the end. Only real programmers will understand anything, and they will probably misunderstand how to use it. So you have to create a message and have to explain it. I was not good at that. I used this for a long time, which is very accurate. It's a general purpose programming language. It has a bias towards systems programming. Never claimed it was universal for anything. It's a better C, and I can explain exactly what I mean by that, mostly notational and type support. It supports data abstraction, supports object-oriented programming, supports generic programming. Okay, you lost every manager about there. This is just too complicated, too accurate, and in some sense too geeky. It took me a long, long time to realize that that is not sufficient. People want something conventional, simple, popular, and wrong. I don't think you can catch me ever having said that except in some kind of snarl or some kind of apologetic thing that this is one thing that's supported, but it isn't the whole thing. And people kept sort of saying, oh, C++ is an object-oriented programming language, but you know, if it had been, it would have been a bad one. Because one of the things people gave a lot of criticism for was not restricting it to writing these class hierarchies that was considered the important thing about object-oriented programming. So basically, so many people conclude that C++ is an object-oriented language. That must be what it is. But it then follows it poorly decide. I mean, you can't be C compatible and fully object-oriented. It's just impossible. And anyway, a lot of the most effective C++ techniques by design, by aim, was classes that are freestanding, point, complex numbers, a vector. They are not part of a class hierarchy, never were, not meant to. There's a lot of non-virtual functions because a lot of stuff is not meant to be overwritten. There's freestanding functions. I never actually understood why something like a matrix vector multiply should be a member. What should be a member of? It has to be a member in two places for starters. And this is not what it's fun for. Freestanding functions, I'm perfectly happy writing square root of 2, provided it gives me the right answer. I don't actually want to say 2 dot square root. I mean, you can do that, but you know, I mean, for those, we've just spent sort of 20 years in school doing it the other way. And I wanted generic programming. I really wanted to be able to have my vectors parameterized with all kinds of good stuff, and I'll get further with that, but certainly the element type. So all of this here, if you go with what I said, it makes sense. This is what it's supposed to do. If you go with that one, it's a mistake. And I found that with C++ spreading like wildfire, I totally lost control over the message. And you can get very nice textbooks, a lot of you have seen them, at least they claim to be very nice, that pushes this view like mad and makes sure that people write bad code, by and large. Horrible, horrible. You know the dragon book, right? Sometimes the dragon wins. So I'd like to talk a few language myths, something I hear all the time and I don't believe. So people say, we want a simple language. No, teachers want a simple language to teach. A language should be something that you can teach in a semester or quarter, and programming, after all, according to many teachers, is a low-level skill that should be gotten over whether the smart students can do it on their own. No, they can't. They can write bad code on their own. But anyway, so they want the simple language for teaching. Researchers want the simple language to manipulate. And what do they do with the manipulation? They usually go immediately to extend it. So the simplicity is just a temporary stage while they improve it. They don't really want simplicity because then they wouldn't start expanding it. I mean, essentially all languages that has succeeded on a large scale has doubled, trebled, quadrupled in the process of becoming acceptable as a tool in general. We see that for all the languages. And programmers want a simple language to start using, but as soon as their needs grow, broaden, change, they want a comprehensive language. And that leaves a lot of problems there. And so languages grow, and everybody I talk to, they want a simpler language. Of course, C++ is too big, it's too complicated, and always was. And there's a lot to be said for that point of view. But how am I going to fix it? Well, I'm going to just add one or two features that, right. If we had a little vote in here about what you wanted, I think your wishes would be roughly in that direction. Make it simpler and add my favorite feature or two. Not all myths are believed by all people, and of course, not all myths are untrue everywhere. This is true for the myth I'm going through here, just a caveat. If you think I've exaggerated, that's possible. It's not deliberate, but I have simplified the message, and I do know that you have to have a caveat somewhere. Language myth. We want an intuitive notation. Well, people confuse the familiar with the symbol. They actually, by and large, want features that they know and love and they've done before. And if you try to do anything new, people want loud syntax. They really love syntax. The uglier, bigger, the better, because it's explicit, you can't get it wrong, etc. So people want to write things like template, type name, container, okay? Template is prefix, keyword, you can see something new and strange and dangerous coming along. And then you have to say container is a type. I called it class at the time because I'm a bad typist, but you know, people insisted we need a big name to show that a type is coming along, and then you can sort the container. This is what we're getting now. And this was what I wanted, but I couldn't get it. Similarly, try it with exceptions. Exceptions were new, unknown to most people. There was languages with exceptions, but not that many. And so people wanted a try block with curlies and a large cache clause, and they wanted to use them all over the place. I mean, people thought that try blocks were cool, and you should put try blocks everywhere. Litter your code with error handling code. I think it's absurd. Okay, that's what I want. F of x. And in the unlikely event that something goes wrong, the exception is thrown, and it would be nice if everything was handled automatically, which it usually is in modern C++. I'll get to that. So basically, and here is allocation over in the free store. Big, complicated things you have to think about. And people do think it's important to put a keyword there all the time. You know, I actually want to say that I want an A that's of type X initialized by 2. That's about as much as I would like to say. And you can do that in C++. You could do that in C++ from day one. In C, you have to put struct in front of the X because there was a time where data structures, structs, records, were new and complicated, and you have to put them in loud. People say they want intuitive, simple notation, and that only works for simple and intuitive things that they've seen a million times already. If you're actually dealing with large numbers of new people learning new things, you have a lot of trouble keeping things simple in the syntactic sense. Then everybody screams for efficiency. I mean, I come from the systems programming world, I come from the C++ world, and people can count cycles and bytes. I mean, I recently had some colleagues that had lost 150 nanoseconds, and they really needed to find them. and this is no joke, this is a fact. This is today. Imagine when your computer had less than a megabyte of memory, and it could do, almost 1 million instructions a second. People were rather upset about this. There was a time where C++ ran systematically 3% slower than C for the equivalent code. In some cases, not all cases. This was considered a disaster that, in my opinion, could have killed C++ in the crib. It took me 3 days to get rid of it. You can't afford that kind of stuff. It was quite a rough thing. So people want an efficient language. Actually, most programmers, most of the time, just want convenience, and they don't care the slightest little bit about how slow it is. If it's 25 times slower, 50 times slower, and it saves them half of the time, they're perfectly happy with that. Not everybody, not all the time. On the other hand, similarly with the performance fanatics, they have their place, but not all the time, right? Most programmers can't even measure accurately. They don't know to a factor of 10 how long their code runs or how much space it takes up. But again, C++ is actually for the people who can tell. Most researchers actually prefer an inefficient language because it's much easier to get a paper for improving inefficient language than for doing one that can do it. I mean, I have seen tons and tons of papers showing how you can make Lisp run almost as fast as C++ and make Java run almost as fast as C++. I mean, dozens and dozens and dozens of papers. You can't do it with C++ because, well, it was fast by design, and it pushed some of the burden onto users, fine, but it was supposed to deliver on fairly small machines, fairly slow machines, by good programmers. For many applications, we actually need an efficient language, but not for everything. Distributed fat can mean that it's convenient, but you can never get down there. A memory model that is inherently inefficient, too much memory used, too many interactions, you just are not in the race when it comes to, say, doing the signal processing for one of those guys. Okay, language myth. We want a language for writing reliable code. I mean, obvious. Our world depends on this stuff. How could we not want reliable code? But it's not what I see people actually do. They say it, but they are really intolerant for any inconvenience that gets in the way of sort of their convenience. That's where you get the security bugs from. That's where you get the reliability bugs from. A combination of being fanatical about efficiency, even if you don't know what it is, and then being intolerant to inconveniences creates a lot of trouble. And they don't like to learn new concepts. There's a lot of people that have learned how to program sometime, and there's something they're happy with, and you meet them 20 years later, and they are very, very resistant for any new ideas. As a matter of fact, when you get freshmen in university, you get people with that attitude. I've been taught C++ for 2 years in high school. I know how to program. I mean, why are you teaching me something new? We're only 2 weeks into the course. This has happened to me repeatedly. I figured out what the answer was. Welcome to university. Anyway, so most programmers don't care. There's not that much professionalism in our field. When the manager says ship, people ship. They don't resign. They have no recourse anyway if they wanted to, because you can't say you have violated the official programmer ethics or something like that. There isn't such a thing. I think there should be. I think if you're asked to, say, ship the software for one of those and it isn't ready, you should be able to say no, and if you got fired or penalized, you should have a recourse. That, by the way, is a distributed computing system with wheels. About 250 processors. And of course, I have a slight bias when I pick the pictures. They tend to be C++ systems. That one isn't. Another myth here. There is a best language for everybody and every task, and one size fits all. There's so many people who really, really want to believe that. And I think it's very, very wrong. It's just a mistake. And these myths confounds education, where some people teach it, and they just can't get it right. Practice, because people apply tools where they don't belong, because they've gotten into their heads that this is the one true tool. Research, there's enormous fads coming in. You're always trying to find the next solution that's going to solve everything. Language design, yeah, all the languages are searching for that. They're expanding out of their niches, trying to become the universal language. Management believes that, and that controls funding and things like that. Very bad, very bad. And you have to have a message. I think I've emphasized that already, but basically, what's the language for? Who's the language for? What would actually improve the language? If you can't answer that question, you've become a fanboy. I probably know more about what's wrong with C++ than anybody else. I also know how to compensate with it, and I'm working hard to improve it. But if you think your language is perfect so that you can't say what would improve it, or what roughly could improve it, or which problems you would like solved even if you don't know it today, you haven't been thinking about that. Try to be specific. And basically, can't do everything for everybody. C++, direct map to the hardware, zero overhead abstraction mechanisms, and it's always been primarily industrial. It rewards people who actually has some idea of what they're doing, and people who has problems that require some attention. So people say, why can't I write my web pages in C++? One, you can. Two, why would you want to? That's not what it's specialized for. There's lots of languages that are specialized for that job. Do you want to write your device driver well, mention your favorite web language. Okay, fine. So in 1989, it's about 10 years into this, two guys turned up at my office, one from HP, one from IBM, and explained to me that I really, really wanted to standardize C++. And of course I said, well, it's not finished and it's still researchy and such, and they explained to me that it's important for their companies and for the infrastructure of the world in general. You simply can't have a language of that importance controlled by a single firm or a single individual. You couldn't trust the firm and said, of course, we can trust you, but you might get run over by a bus. And so, yes, I really want to standardize this. It took about an hour. So basically, I think it's a necessary evil, and it's really painful to go through the standardization, but you have to have something that's stable. Stability over decades is important. There are programs that last only a few years, but the programs that last for decades, you need some kind of standardization. They told me you can't have a major programming language controlled by a single company because you can't trust a single company. Of course you can, and some of them are successful, but you notice they change rather frequently, and they sometimes get biased in favor of their owner and things like that, and I don't like it. I worked for a company that was a net consumer of software, and so we wanted to have multiple suppliers and have different suppliers of language technology, and one is stable. There's lots of kinds of standardization. What I'm talking about here with C++ is the ISO standardization, which is probably the most rigorous and the most painful to deal with. And we want vendor neutrality. That's totally impossible in total, but you can approximate it by a good standard. that actually has importance because the vendor neutrality is important for the major users, but it deprives a language that is vendor neutral of support and funding, because the vendors will do things that gives them a differential advantage. Sort of the strategy of the commons. If it helps all of you, we have no money. If it helps us over here, and especially if it leaves those guys in the dirt, we have lots of money. And that's the way some of the proprietary languages grew. Okay, so let me say how the standardization is done. There's 100 members at a meeting, and you have to agree, you have to reach consensus. That's not easy. And there's another 200-300 more on the web. So it's a fairly vigorous debate, and it's really hard to focus. As I said, it's painful. It's primarily industry players. All the major guys are there. It's a very democratic process, roughly one company, one vote, and then it goes to one nation, one vote at the next level. There's no technical qualifications required. Most people are experts, and the rest think they are. The aim really is consensus. Winning a vote 60-40, we don't consider acceptable. That is almost guaranteed to create a dialect for somebody who doesn't want to follow it. It gives good excuses for raising the issue, and then you have to deal with it again. I prefer sort of 90-10 and most of the things we get. And committees are really good at adding complexity and delays. They have no coherent view, so they go in all directions, and this is difficult. And it's hard to say no because, well, then you build up enemies and things like that. And so you can look up WG21, that's the official name of the committee, and you will find all the information. There's all the documents going back to, I think, 91 or something like that. It's there. One of the problems that you have to deal with is compatibility. If you're not a new language anymore, you have previous versions. C++ came with a built-in compatibility problem. You have here the growth of C, BCPL through B to KNRC to Classic C, and I took Classic C and C with classes and made Simula and Classic C, giving me C with classes that got renamed to C++ when people were starting to call it C, and that was considered a problem. And there has been a lot of borrowing forwards and backwards. There's one standards committee working here, one standards committee working here. They can't agree on very much. So there's endless catching up and repair work. I mean, you know, organizations' primary directive is to perpetuate themselves. Ever known a committee that closed itself up easily? Well, we have two committees here. And so you get all of these overlapping sub and superset each time one of the languages change. This is my nightmare. Notice we, by the way, are at C++ 14 now. That's fine. Okay, so there's another way of doing it. You can take these problems with compatibility. It's a feature. Stability over decades is a feature. It's valuable. But boy, it's expensive and hard. It's hard to correct mistakes, and it makes people very conservative in what they add and how they add it. It's a real pain. But the alternative is something like this. Here's another chain of work here, which is basically the Viet languages. Pascal, object Pascal, Pascal 2, modular, modular 2, Operon 2, Operon 7. I don't know if there's any compatibility down there, but there is no compatibility in the other areas. Each time a new language comes, you have to sort of either maintain the old compiler forever, which they don't, or you have to rewrite your code forever. Are we up on the time limit? Okay, in 2 minutes I'll stop right after this slide, and then we can leave. But basically is there's an advantage. You can grow easier, you can have elegant things, you can get rid of old mistakes and such. On the other hand, your user community is cut down every 5 years to about 0. This one here is a right pain in the butt, and there's features in C++ that Dennis Ritchie considered a mistake in before we even got to KNRC. And we can't get rid of them. There's somebody that depends on it somewhere, or at least they claim to be. We need better tools to upgrade this stuff, but we haven't had them yet. That's a hard problem. So that's the compatibility thing. So let's see, yes. I'm going to stop for two or 3 minutes here to let people who needs to go. Interlanguage operability was important from day one. I tried to make sure that you could have linkage to C and Fortran. Interoperability was an explicit aim, and it sort of worked. You don't actually pay to any cycle or byte to convert to pass data to and from C and Fortran. It's a really big problem, though, with many, many languages, and it takes two to tango, as it says, and you can't be interoperable with somebody who doesn't want to interoperate. And this is actually quite a significant problem with a lot of languages. The new language comes, it's going to take over the world, everybody's going to use this new language, so it will allow you to call the old language from it, usually with complications, and they won't let the calls the other way and things like that. Oh, there's a lot of problems. And basically, I mentioned teaching as a problem before. I actually think that a lot of C++ teaching is so misguided that it does serious harm. The C first idea, it teaches people a lot of ways of getting themselves into trouble with pointers and casts and macros and stuff. Before they actually learn the alternatives, that means that they don't have to do those things. Similarly, the pure object-oriented programming, people built huge hierarchies, and they noticed that to use them, they have to use all kinds of casts and other horrible things to deal with. So that's bad. Anyway, if you feel the urge to write a macro, try and desist, because either it's the language's fault, and I'll try and fix it, or it's your fault, which is more likely. And you've seen a lot of C++ code that has macros in it. I see two uses of macros in C++. One is to deal with old compilers that doesn't have the features for the alternatives, and that forces people to macrotize some of their libraries. And then source control using ifdefs if you don't have a source control system that allows you to deal with the versions that way. Okay, community. One of the things that C++ never got right was to have a community. There's never been a real center. For most languages, there is a website you can go to for information, for libraries and such, and there's a community that decides how does libraries look, how do they communicate, what is the common style. There's none of that for C++. Instead, there's a lot of little empires. There was, in the early 90s, at least 20 companies that thought they could own C++ in some way or other. And they generously guarded their community. And they had their own libraries and their own tools, their own users groups, etc. So the whole thing was fragmented. And some of these little empires are not so little. I mean, usually hundreds of thousands of users. And so they're different with. But basically, that's where sort of the money goes, not for the language itself or work for the common good, for particular little empires. You're not a C++ programmer, you're a Borland programmer, a Microsoft programmer, IBM programmer, even if most of what you did was the same. And the corporations really prefer languages they can control. One of the interesting things is that the number of C++ programmers, despite that, is still growing. It was growing very fast for the first couple of decades, and of course it slows down. But you know, the numbers says we are up 100,000 programmers last year. It's a small percentage of the community, but it's still a large number. I mean, if you can pick up 100,000 programmers, you must be doing something right. Okay, I promise not to boast. That was probably the closest I came to it, but it was a fact. Okay, let's look at some code. And so I've been talking about the problems and the sociology around the language things, and let's look at some code. Resource management in particular. So basically a resource is something that has to be acquired from somewhere and has to be given back. Explicitly or implicitly, though you tend to acquire things explicitly and you would like to give them back implicitly because then you can't forget to do so. The reason you have to ask for them is that's the way you get exactly what you want, no more, no less. C does this. There's local variables for built-in types. Then you use malloc and free to get free store. There's pointers to all objects, and the manual initialization and cleanup. It's all, you have to do it. Simula, local variables for built-in types, whereas you have to go new to get over in the heap or dynamic memory, you use new. And references to dynamically allocated objects only. There's a manual cleanup, some support for initialization. There's garbage collection for cleaning up your memory, but that's not quite enough. So for C++, the thing that I did immediately, and I think I got right, was local variables of all the types we have, independently of who did them. New can be done for all allocation. Delete has to be explicit to give it back to the free store, but there's an implicit cleanup. The destructors fire to clean up any resources for what you did. And the idea from day one was to reduce the number of explicit deletions. And I used to say that I can keep track of 10, and if the number goes higher than 100, I make mistakes and you have to automate it. People didn't believe me, and there's lots of programs out there that has tens or 100,000s of deletes in them. My rule of thumb is if there's a delete, there's probably a leak somewhere, or worse. And actually, if there's a new, there's probably a delete somewhere, and therefore there's probably a leak. So you need to control the use of new and delete. But anyway, people keep using the Simula and C styles, and sometimes in mixtures, and the results are not pretty. We have to do better. I'm going to show you how. So basically, you don't want resource management to be manual. I think everybody would agree with that. If they don't, they should. We don't want leaks, and if it's manual, you will get leaks. That's what I think is experienced. We don't want complex resource management code. So pointer manipulation, lots of cache clauses, dispose idioms you have to remember, have to do try-catch to manage your resources, just doesn't work well, doesn't scale well. And one of the reasons garbage collection is not enough is that resources are not just memory. A resource is anything you have to require and release. That means file handles, thread handles, locks, and things like that. And we need a mechanism, we have a mechanism for that. Constructors, destructors will deal with it, and resources should have an owner. So basically, if you can have a handle to all of your resources and have them scoped, nothing will get lost. It'll all eventually get cleaned up. And usually at the minimal time. You don't want high resource retention either. I mean, if you keep your objects around for twice as long, you need roughly twice as big a machine, right? And it doesn't matter if you're not at capacity of your machine, but if you are dealing with a server farm, doubling your resource retention means you need another server farm. They aren't cheap, and they're not cheap to run. So things like that matter. And so we need, the ideal handle is a well-defined and useful abstraction. This could be a vector, it could be a lock guard, it could be a file handle. It has a semantics to it. We'll get to what it isn't. So basically in the C++ standard library, you find all of these standard abstractions that fit this pattern. They take care of their elements. And there's other things, thread locks, guards, streams, and some smart pointers. Notice that the non-memory resources are important. These are non-memory resources, but some of these here have a vector of vectors of strings you have to clean up preferably effectively. So you can't just, a garbage collector will do some of it, but not all. So basically the idea is to control the whole life cycle of an object. Constructors for the creation of an object, destructors when you get rid of them again, copying, movement, I'll talk about that, access to the representation, and we need to get the cost down so the fanatical C programmers cannot outperform it. And they don't anymore, not when we use this well. I've seen that on an industrial scale. Here's sort of the code example of it. I mean, we have a vector of cheese. We have a constructor, which happens to take an initializer list. We have a destructor that cleans up any mess left behind. And so there's a representation here, which users can't access directly, but that takes care of it. So of course, the manipulation of those elements, the new and delete, are in here. In specific, the resource handler controls it, not the user. And so I can say I want a vector of doubles initialized to those well-known constants, and a vector of strings of some language designers. And the point here is when we get down here, the end curly, all of these resources are released implicitly. You don't have to write it. Somebody is saying that this is their favorite C++ language feature, the end curly, because that's where all the magic happens. And if you leak resources out of a local block, you probably leak it completely and it starts getting complicated. If you can keep it local, things are easy. So let's see what people actually do. I mean, this is nice theory, but because of education and history and such, that's not what people do. So here, I find a lot of code that looks like this. I find more of it these days. I mean, here, I want a new gadget. And when I'm finished with the gadget, I delete it. And then people scream for their garbage collector. Anyway, look, there's trouble. I'm throwing an exception. This gadget doesn't have an owner. There's just a pointer to it. Nothing is happening when you leave there for this one. Similarly, you don't need exceptions to get into trouble. A return statement will do just fine. It leaks, like anything. So basically, we need to get rid of such code. It's bad. And as I said, my rule of thumb is I saw the delete, then there's probably a problem somewhere. Yes, there was, right there, right there. And even better, I can see the new, so there's something wrong. Anyway, okay, so let's deal with it. We have sort of a garbage collection mechanism in C++11. We just make a shared gadget initialized as appropriately, and we get a smart pointer out of it. This is the C++ feature of saying take the type of your initializer. And by the way, that's a static type. There's no overhead in this. It's just flexible notation. So basically here we have a garbage collection mechanism, except that it works. It works by calling the destructors quickly so that things are cleaned up. No excess resource retention and no leaking of, say, locks and file handles. And so here, if you throw the smart pointer here, will have its use count decreased, and it'll go away. Similar here, similar here. But you know, why am I using a garbage collector? Why am I generating garbage in the first place? This object is mine, all mine. I didn't give it to anybody else. There shouldn't be any garbage here. Okay, we can deal with that. There's another kind of smart pointer in the standard library called make a unique pointer, so you can make a unique one of this. Everything happens, except there's no use count. Use counts are actually unpleasant. Basically, memory management with counted pointers are unpleasant because the use counts has to be synchronized somehow. There has to be some kind of locking mechanism for the access. So here, I'm pessimizing things. I'm not sharing anything with anybody, and yet I have to probably not take a lock. At least it'll be lock-free or something, but manipulate an atomic or something like that. This is overhead that is violation of most of my best principles. So you can get rid of it like this. This is fine. But you know, and the new and deletes have disappeared, so that's good. But there's still something wrong about this. I mean, why do I use a pointer at all? That's the way the code should look like. It was a global variable. It's just that people have been taught in school to write new all over the place. And I mean, those of you who have seen a lot of C++ knows that this is not that uncommon. It should be. There's absolutely no reason for writing that stuff. Okay, so we can get rid of this. That leaves one problem with the approach that everything has a scope, everything has a handle. It is we need to be able to move things around between scopes without cost. And traditionally, when we copy things out of a function, when we copy things over into another scope, there is a very significant cost with it. Say you have here, this is the way a large object looks. It's usually got some kind of handle with a pointer in it, and it has a large object that it keeps track of. Say this is a 10,000 by 10,000 matrix or something like that. And what we really want to do is we take something, a fairly standard factory function. This is a matrix that it adds. In other words, it creates a new matrix that holds the sum of the elements of the other two matrices. It's just the simplest factory function I could think about. Code are absolutely littered with factory functions. And notice people very often return something that it has reference semantics. It's a pointer or something like that. And that means that you now have to deal with memory management and things like that. No, we should get a matrix out of it. It makes a new matrix, and we'll get it out. And the way we do that is very simple. Remember how the object was looked? Look, there's the handler, there's the memory, so we just steal the representation. Now there's R, right? So we steal it and put it into res, and then we cut it off there, so the matrix is now empty. So there we get 10 million doubles out at the cost of 2 assignments max. 1 if we got a good optimizer. Word assignments. So that solves the last of the sort of the problems of this view of things. So basically, so why do we use pointers and references and iterators, whatever you call these things that point to an element? Traditionally, in C, we have used them to represent ownership. That doesn't work. It leads to leaks. Just don't do it. If you have a naked pointer representing ownership, there's something wrong in your code. So to reference resources from within a handle, all of this stuff I'm showing and talking about is built on top of the basic language. Vector is not a built-in type. Thread is not a built-in type, etc., etc. So you use the pointers inside resource handles, and we represent positions. Have to be careful not to get them wrong. To pass large amount of data, you can do it by reference, by const reference, works really nicely. Or to return large amount of data, don't use move operations. That's new in C++ 11. Some of us were doing tricks to do that before. We've always been able to do it. It's just been too hard to recommend it as a systematic strategy. So here's a piece of C++ 11 or 14, as it will be now. Basically, I want to find all elements in C that has a value equal to V. And what I want to do is I want to give back a vector of pointers to the whatever element type there is. We call element types value types fairly systematically. So here, I make myself that vector, I fill it up with good stuff, and I return it. So from just this, you'll see that in C++ 98, this would have been a performance bug of the first order. What if the container has a billion elements and you return 10 million pointers to 10 millions of them? It's not too unrealistic. Okay, so here it isn't. That's a move operation. The cost, since a vector is 3 pointers, is either 3 or 6 word assignment, depending on your quality of your optimizer. It doesn't actually matter too much whether it's 3 or 6 in real code, because either there's not enough work done so that it wouldn't matter because you have infinite time, or you do more, so the difference between 3 memory accesses and 6 doesn't matter. Most of the time it'll become 3. We're pretty good at the optimization. Inside we're using a range for loop for all C in X. C if X equals V, that one here, and we just fill up the vector as we go along. Yes?
But you actually should be aware that those references will not outlive the original vector. So though, you shouldn't pass those references if the original vector is already deleted.
Yeah, I mean, this
Could you
I'm
repeat
finding
the
a set of
question?
pointers. What? I'm not sure if there was a question. He was telling me something, and I'm going to tell him that, yes, I agree. Basically, this is a set of pointers into the container. And obviously, the set of pointers should not outlive the thing they point into. There's nothing in the language that stops you from doing that, just there's nothing in the language that stops you from returning a pointer to a local variable. It's fairly easy to write a static analyzer that catches all of those. And I wish I had one that was really systematic for that. But in my experience, that is not really on my top 10 list of problems. People are aware of it. So basically, here's some code. I make myself a vector. I find all 7s in that vector. And it should have 1, 2, 3 elements, and you could test it. Here, I'm taking another kind of container, a string. Mary had a little lamb. I look all the find alls. I feed them into a for loop that tests whether the pointers actually points to A's, because I'm looking for A's, and if not, it's a string bug. That's a test program. This was just a little example of what modern code can look like, in case some of you haven't looked at C++ for a decade or two. This is not C++, well, 89 or thereabouts. There's some syntactic convergence that I have noticed. All the languages have a way of sort of picking the type up from the initializer. This is Python, this is C++. And they all have a for each loop. This one is the C++ one. Oops, that's a 14 one that didn't pass through, so I should change this slide again. I have to say auto there. And you do the operation, you return it. They're sort of line for line similar. The most difference actually here is just a sequence. They don't know, there's no type here, and you can use one of these new type systems we hear about here, but traditionally you could just pass anything to it. In C++ 14, you'll be able to say it should be a sequence. And that's the only kind of arguments we want, and we do the type checking here. And so I showed this once, and people said, but he's an idiot, he doesn't understand Python. Nobody would write this. That's right, nobody would write this either, but it's an example of how you use the basic language features. In both cases, you would, of course, use the standard library. And the convergence is there. Accumulate takes more arguments, but you can easily shorten them down. And so it's still the same. So I think there's a certain amount of convergence going on, which is interesting, I think. And people say, yeah, that's not C++. Concepts is a technical report. Should have the final vote on the 20th next month. The version of Accumulate I wrote, you just write it like this. And most languages simply don't have an ISO standard, so this discussion about whether you could do it without writing your own code is rather meaningless, because yes, this was mine and not in the standard, but if you don't have a standard, then there's no problem. So I reached the end of this, and thanks to our hosts and the quick reorganization of things, we have lots of time for questions and discussion. We ask that when you ask questions, get a microphone so that everybody else can hear what you're saying and that they can get it for the record. Yeah.
Hi, thank you very much for coming to Carry On and giving a very interesting talk. Out of the new languages, like the languages that have been proposed and designed the last, I don't know, decade or so, are there any that have kind of got you excited, or you said, wow, that's really cool?
There's lots of interesting things going on. After being in the field for many years, it's hard to get really excited because most of the things you have actually seen before. And a lot of the hard problems is not in getting the idea, getting your first academic paper, getting your first user. It's very exciting, but once you're looking at it from the outside and you've seen it 100 times before, it's sort of less exciting. And a lot of the ideas you've seen before, it takes a very long time for an idea to work its way into a tool. And when we look at serious tools, I'm sort of less interested because I'm not using them, and I can appreciate the hardship people are going through to get the new languages into real use. Sometimes you see a new idea, but not all that often. A lot of it has to do with polishing it to make them into tools. And I like to look at new languages, I like to try them out, but at a very small scale because this stuff here keeps me very busy.
Thank you.
But yes, I'm keeping an eye out. And sometimes there's something that's nice. But really, no.
So, what is the single most important feature you'd like to see in C++ 17? And how do you think that will affect the language?
The single most feature. I sort of predicted somebody would ask that question. So, as I said, getting a standards committee of sort of a community of maybe 400 people, 100 turning up, have any direction is really, really hard. Most people want what will help them in their current project, preferably this year. And that gives a bias against anything that's important. Because most things can't be done this year. So here's my list. And number one is right up there, concepts. That's the type checking for templates. I'm going to talk about that in the keynote tomorrow. Couldn't fit it all in. There was a longer version of this talk that showed concepts, showed resource management, because in my mind they're very closely linked together by getting decent interfaces. And so type checking for templates, and we're going to get it. I'm really quite convinced of that, and they're very, very simple. They're type predicates, basically. Predicates on types and values. So we'll get it. So if you've seen these multi-page horrible error messages out of templates, they're going to go away. And the next thing on my list is modules. I want C++ to compile faster. The current experiments, mostly at Google and Microsoft, shows, well, I don't officially know, I don't know all of the numbers, and I don't officially know most of the numbers I do know. But people have had experience where compilation speeds have increased by just 20% and by 100 times. And the mean, which they won't tell me, I believe is between 5 and 10 times. So if I get my compilers to speed up by 5 to 10 times, I'll be very happy. So that's number two. I want the standard STL, the containers and allocator containers and algorithms and such, I want that with concepts in it. And I want ranges. I really don't want to say sort of v.begin, v.end. I mean, my code is called sort of v, and I would like to get that into the standard and properly type checked. That I'm pretty sure that's coming. There's a very nice proposal in great detail by Eric Niebler that does this. I would like to have uniform call syntax so that I don't have to decide between x.f and f of x. I can do that technically, it's not that hard. Getting it through the committee is very, very hard. We'll see. Coroutines, that was my bread and butter for 10 years, kept me busy, and gave C++ applications an edge. We're going to get them back again, very simple ones. Network support, maybe contracts, that's a little bit harder, but we're probably going to get it. We'd like to get some parallel algorithms and some SIMD algorithms, libraries supported by primitives, and more basic sort of vocabulary type in the language. And then I want to be able to put arrays on the stack without having overflow problems and not knowing the sizes and things like that. Now, the star means that we'll make progress on it this year. In other words, they're moving, and I still believe this can be done. This is not quite the answer to your question. It's an answer to the bigger question. This one is number one. The others are sort of not sorted in great detail. Here is a lot of the performance work. Okay. Oh yeah, there's where you can get information. cpp.org is the new sort of C++ Foundation website where there's a lot of information there. I have some books that are up to date. Oh dear, that's the old book. There's a second version out using C++ 11 and 14. That's the current one. That's the 180-page summary of the whole thing. And there's the committee's website that has all the proposals in it.
Yeah.
Oh, yeah.
Thanks very much. In the early days of C++, was there anything you did to try and popularize it? Like, how did it kind of get off the ground?
That's sort of very peculiar, really, because there wasn't any marketing organization, Zippo. And, well, no, let's be really correct. I once had a marketing budget from AT&T, and it was $5,000 to be spent over 3 years. And when I first went to Uppsala, we could just afford to hire a booth. They were cheap. We could not afford to bring a computer. And we borrowed a blackboard. And we didn't have any brochures. We had a sign-up sheet for some of my articles. That was it. And I guess I must have been persuasive, because that's all there was. There was some talks and some papers and a cheap but not free compiler. And then just worked hard providing good maintenance. The standards these days are much higher. I mean, nobody would try a general purpose programming language with that kind of backing. Roughly one guy with a couple of friends running it. But it worked. I actually think that the reason it worked was that it found a niche, which was this niche of being close to the hardware, high performance, small, and ability to handle complexity. I once got a letter on paper from somewhere in Central America saying how much they liked C++. And so, of course, I wrote back saying, this is very good. Why do you like C++, and why did you choose it over alternatives? And the answer came back, it's the only language that can run, that can do things like that can run on computers that does not require air conditioning. And so the ability to operate in hostile environment, the ability of people to port it themselves, the ability to deal with weird hardware, that kind of stuff was important. It wasn't marketing, it was hitting a need. And most people who design languages want to do something much flashier. I remember fuming at the time. You go in and there's these 10 languages being presented. I mean, it's not trivial languages like Ada and Smalltalk and Lisp and such. And everybody promises we can do things 10 times better than you can do today. And here am I saying, I can probably double your productivity. I mean, but I delivered. And factor of 2 is worth having. And by and large, then you can deliver another factor of 2 later. But it's quite, I considered it very important not to promise what you couldn't deliver.
Hi, I teach C++, and in the recent years the material is rapidly growing. And even when concepts will go in, I believe students still need to know about templates because they will see that in legacy code. So I would like to ask for your advice.
Okay, now, where was it? I found myself in charge of teaching freshman programming at TAMU almost 10 years ago. And I thought it would be easy, and I looked at the textbook and came away screaming, if that's C++, I don't like it either. And struggled the first year and basically wrote a course from scratch. And that's the book based on it. So that's my exhaustive answer to what I recommend. This is something that you can teach freshmen to program reasonably well in. If they work hard, they will succeed, and you can make them work hard. The way it's done is you start fairly conventionally. Data types being bool, char, int, double, string, and vector comes in the next week. And then you just teach them how to write loops, what an algorithm is, what a function is, what a class is, and what I/O is. And then you show them a little bit about building hierarchies for graphics and stuff. Then comes the interesting bit, which is where I take vector apart, show them how vector is built. That forces you to deal with free store, dynamic memory, new and delete, which I tell them belongs in constructors and destructors, so that you don't get into trouble. Actually, that's chapter 17. They don't see a pointer before that. And I teach them how to deal with exceptions. They have used them, but here they can throw and defend them against them, RAII, that kind of stuff. And then I teach them how to parameterize with a type T. That's where template comes in. So that happens. And after that, I teach them the standard library, and then I give them a history lesson. And after that, we are out of about 3 months. That's a semester. And I have done that successfully almost 20 times. It has been run at TAMU. And we have a greater success rate than we did before, which may not be perfect, but it's pretty good. We don't lose very many. And a lot of them actually learn something about programming, not just programming languages. It's not, notice the title, programming. There's a little C++ down there, but it's not a C++ course, it's a programming course using C++, in other words, programming the way I'd like to see it done. But the emphasis is on programming techniques and how the language supports them. And so I can recommend looking at that. That's my approach. And it's been refined and developed over the better part of a decade. It's not just me, it's other lecturers have given it, and I believe it's in use in at least a couple of dozen places in the world.
Inheritance and polymorphism was not in that list that you mentioned.
I mentioned it. I mentioned class hierarchies with graphics. It's sort of in the middle. As a matter of fact, I slip it in. People are so tired after me teaching programming techniques and then some boring I/O that once they get to do the graphics, they're so happy that they don't notice that I'm teaching object-oriented programming. And I do build the hierarchies. I do make the distinction between interface inheritance and implementation inheritance and tell them about how to use it. Most of that goes straight over their heads, but it's there when they come and have to use it for real. They've seen examples of how it's done.
Thank you.
So I guess part of his question was, should old styles of C++ still be taught? I guess your answer to that was just briefly in the history lesson, or?
No. I should have mentioned that. Sorry, I didn't. The history lesson really is a history lesson. I start with assembler and work through the languages. I would like to give more of that, but I didn't have the time. But basically, showing the things that led up to C++, which is their main tool, trying to say ideas, problems, people, give a historical perspective, because I think part of professionalism is actually to know where your profession comes from and where. I have two chapters that we sometimes get to and sometimes don't. One is simply C programming, which is how do you write good code using C if you don't have the C++ features? And the answer is partially, this is the way you fake the techniques using it. So if you don't have exceptions, how do you handle errors? If you don't have operator new, how do you do it with malloc and initialization code? There's a chapter for that. And we usually get to it. The other thing where we get down to more traditional code is the chapter on embedded programming, where we get to bit fiddling and byte fiddling. But I consider that a specialization. So there's chapters on string manipulation, mostly regular expressions, and hash tables, using the standard hash table on O.map. And then there's one on numerics, mostly a matrix class, and a few other things. So basically, we do about half of the book, and the other half is there for people to pick up if they need for a particular project, or if we manage to get to the end early, we put in another chapter or two.
So I guess a follow-up question is, if you taught the most recent flavors of C++, wouldn't students feel a bit disheartened when they go to a lot of C++ out there and it doesn't look like that?
You're right, there will be, and that's good. I mean, I'm still an idealist. If they come out and I find that people really haven't caught up, I want them to create trouble. And sometimes it works. Sometimes it doesn't. Maybe they get too disillusioned, but I actually think learning how things can be done right, not just shown, do it this way, but saying, if you do it this way, these are the kind of problems you solve, this is why you do it this way. And if we get to the C chapter, which we mostly do, then they'll actually have seen the technique of saying, oh, I can't express my programming in my language, I have to somehow fake it, but I still know how to think about it.